In the last lesson, we looked at how you calculate the work that's done by a constant force. We saw that work was equal to the amount of force times the displacement of the object that the force acts on times the cosine of theta, where theta is the angle between the force and displacement vectors. But what if the force is varying? What if the force is not constant but changes as the object moves along? So in this plot, we're showing the varying force that might act on an object as the object is displaced. So as it moves from an initial to a final position, the amount of force that's applied changes. Now, we can think about breaking this problem up into little steps. So imagine moving the object just a very small distance where the amount of force on the object does not change very much. Then if we multiply the force in the direction of the displacement times the displacement, that actually is the area of this little rectangle. Now, you can imagine making these rectangles narrower and narrower, looking at smaller and smaller changes in the displacement. And if we are to do that, then the force for each one of these little rectangles doesn't change by very much at all. And the area of each rectangle, if we add them all together, becomes a better and better representation of the amount of work that's done on the object. So in conclusion, we can see that if we have a varying force, the total area under this curve, which is better and better approximated by these little rectangles as we make them smaller, is the amount of work that is done on the object by the varying force. Now we can apply this idea to figure out the work that's done when we stretch a spring. So imagine we have a block attached to a spring and we stretch the spring from its relaxed position to some final position. The amount of work that we have to do in order to stretch the spring is going to change as the block moves, because the more and more the string is stretched, the harder and harder we're going to have to pull as the spring pulls back. So we're going to have to exert a pulling force equal to the spring constant times the displacement, and as the displacement changes, the pulling force that's necessary is also going to change, because we have to balance out this increasing spring resistance force. So if we want to know how much work we are doing in total pulling the block, then we know that we have to find the area under the force that we apply versus displacement curve. And we can see in this case that curve is a straight line, and it's a straight line with a slope equal to k, and it increases as we pull the block further and further out. So this area is actually a triangle, and we know how to find the area of a triangle. It's 1/2 times the base of the triangle times the height. The base of this triangle goes from 0 to that maximum displacement, so that would be x max would be the length of the base, and then the height of the triangle is what we get when we plug that maximum value into the force equation. So that would be k times the maximum value. So simplifying this expression, we get 1/2 kx max squared. And so this becomes the amount of work we need to do in order to stretch a spring out a distance of k max from its relaxed position. So here's a question where you can figure out the amount of work that's done on an object by a varying force. So the graph is showing a force versus displacement graph, and we want to figure out how much work was done by this force.